Good evening and welcome to the fifth FoundationDB meetup. Really glad you can all be here on an evening, taking the time. Thank you. A special thank you to Sarah from Amplify Partners and Rohan for sponsoring this event. Thank you, Rohan and Sarah, who couldn't be here with us. I want to introduce today's speaker. Today's speaker is Ben Collins. Ben Collins is currently the VP of Engineering at Antithesis. In the past, he has held leadership roles at Facebook and Apple. Another really interesting and more relevant tidbit about Ben is engineer number 1 at the first FoundationDB team. So he kind of started it all. And today he's here to talk about deterministic simulation and how that really made FoundationDB a robust piece of software, and how he's taking that piece of technology in Antithesis and how it's going to help teams. So I'm really excited to hear Ben talk about deterministic simulation and how the journey has been from FoundationDB to Antithesis. So let's give a warm round of applause and welcome to Ben.
All right, Arvind, thanks so much. It's definitely an honor to be here. Great to be speaking about FoundationDB. And yeah, I don't know that I started it all. I was there near the start of it all. But yeah, so hopefully, one of the things I'll be able to do tonight is kind of show maybe some pictures and give some stories about some early stuff. I guess that's really like, really my one thing I can really give that nobody else can. So. I tried to find like a picture of like the first room that we were in one of the founders' living room when we started working on this. I couldn't find a picture of that. So anyway, but I have some other good ones in there that I'll put in it. Anyway, it was great to chat with a lot of people beforehand, the folks that are here in person, joining in person. Sounds like we've got a pretty wide variety of folks that are building other databases, talk with a number of people coming out of PhDs. So anyway, there's going to be a pretty wide variety of, I think, experience here. So I'll try my best to get a little something for everybody. All right. So first of all, just to kind of like figure out a little bit more, because I didn't talk to everyone, like who here is like on their team or at their company like running FoundationDB in prod? Like, show of hands. Okay, it's like a fair number, but I see you, Jingy, over there. And then how many people are actually like contributing to the open source project? Like, okay, a number of people as well. All right, great, nice. So it sounds like there's some familiar here. I was gonna show you that actually like I might not have been working on FoundationDB for a few years, but I actually loaded up GitHub. There I am on the project. I'm in the top 100. So, don't have a lot of commits there in the past few years, but I'm still in there. All right, so what are we going to talk about today? I want to give a little bit of something to everybody. So here's kind of like what we're going to do for the agenda. Like, we're going to start at the beginning. I'm going to give people sort of something that a lot of you already know, but kind of a little bit of the value proposition, the idea of like why we did this whole FoundationDB thing from the beginning. Try to give you some of the behind the scenes stuff as well. And then we'll talk a little about, based on that, what we ended up doing for the testing. And so you already mentioned deterministic simulation. That's the DST here. I'll kind of go through what that actually means. It's probably a technique that a number of you are generally familiar with. And I'll just try to give a little more of the rationalization for like why we went after that at FoundationDB. So yeah, I mean, then we'll talk a little bit more about like where it's used outside of FoundationDB today, which is like a quick survey on that. But then like I'll get to another piece here, which is just like trying to take some of these things and roll them together and just kind of like discuss a little more in general, like testing your software. Like I know personally, like if we all raise our hand, like I think we all know we can up our testing game. Like we can get better, we can test more efficiently and all these things, right? So people ask me for advice. I'll try to roll a few things together. I work at a software testing company after all. and hopefully give you something to think about. And then I think we're gonna have time for some questions and stuff at the end. So I'll tell you a little about Antithesis. I won't belabor that too much, and then hopefully we can do some questions. I'm probably gonna have some pretty good ones from this audience. All right. So I started working on this thing in 2010. So 2010 is actually at this point kind of like a long time ago. My oldest daughter was 3 at the time, and now she's like headed off to college. So like that kind of was a long time. So 2010, what was new in 2010? Here's a little quiz for you. It's like a history quiz. So there's a major new product line from Apple launched in 2010. Who knows? Who knows what it was? 2010. iPad. iPad appears 2010, 15 years ago. All right. So okay, now we're going to go a little more towards like kind of the developer tooling. Node.js. How old was Node.js? 2010. Anyone know? Turned 1. It had been launched the year before. So anyway, I just going to point out, like, we've been running JavaScript on the server for 15 years, and like the world is still spinning. So we've survived. We've survived 15 years plus of JavaScript on the server. It's amazing. Okay, now here's what I put this. I was putting this slide deck together last week, which is I was going to actually sort of like give a financial aspect. So I said if you had $1,000 and invested in NVIDIA, I put this slide together last week. So as of last week, you would have had $588,000 you would put 15 years ago. But I think it's changed anyway. I literally was changing so much I didn't even check back in on what it was. So anyway, so 15 years, that was kind of a long time. But what did we want to do at that time, right? The world of databases was honestly pretty different. So we wanted to set out and build a database that had ACID transactions everywhere. Like, we thought that this was something that was reserved only for the top end of databases, but actually made people's development lives much easier, right? I see some nods out there. Like, people really care more about transactions now than they did 15 years ago. Like, and people have come to realize how important it is, okay? We wanted a distributed, scalable, cloud scale, et cetera, from day one, right? So this was going to be obviously already something pretty tricky to build, right? And then we wanted to be perfect, like perfectly reliable. So now some of you run it in prod, maybe it never was perfectly reliable. We wanted to get as close as we could to that. And so then when we thought about building this, there was like really one problem, right? Well, maybe there's a bunch of problems. One problem was we're just normal people, and we like wrote code, but we wrote bugs too, as everyone does, right? And so if we wanted to achieve all these things and have ACID transactions and the complexity of being super scalable, and we're mere mortals, then we were going to write our bugs, and we had to actually go and pretty much find all of them, right? So then we set about saying, okay, well, like, how could we do that? All right. So how are we going to find all these bugs? The first one we thought, like, okay, could we run it more than all of our customers would ever run it? Like, maybe if we ran it like 10 times as much as everyone else would ever run it, we'd find all the bugs first. But that wasn't going to happen, right? We wanted to be a little startup and sell this to big companies, et cetera. So we couldn't just like go and run it at huge scales, 10 times as much, right? Now, another thing, we could like model everything formally, and I know there's some formal methods folks out here. We wanted to build a very big, very complex system, and we didn't think that we were going to be able to formally model everything in this thing, right? So that was also out. Like, I would say, that formal modeling is great for smaller things. Like, if you're going to build a raft algorithm, great, you should definitely formally model that. When you're going to go build this whole big distributed thing, it's going to run out of steam. Now, I know there's some folks working on making that easier and easier, and I think that's great. But we wanted to build something very big and complex and build it quickly. Maybe just like have like an absolute ton of unit tests, right? That also just doesn't seem quite right? And I think we all know like where unit tests are kind of fall short. So, what goes into a unit test? What can it actually be? We wanted to, like, as I said, be distributed from day one and like be able to really test like the whole thing together. So that wasn't going to happen either. All right. So we're gonna have to think of some other thing. All right. So what do we really want? Like, if we could just like spec out sort of our desires, like the optimal thing, our objectives we were working against 15 years ago. I came up with like 4 things that we'd want as like objectives in a testing system. Okay. First, this thing should be fast and debuggable. Like, we want to, the testing system should run quickly, right? And we want to get results quickly, and then we want to be able to debug based on that stuff, right? Seems reasonable. We want to test the whole system, okay? This is kind of where it starts to get tough, because if you want to, what constitutes like the whole system, right? And so I'll kind of get a little bit more into how that adds limitations a little bit later. But we wanted to like get the whole thing together and test the whole thing. All right, the test should be robust, like, and that could mean a lot of things here. What I mean by that is just, we didn't want to just sort of like test the last thing we thought of, or like have hand-coded scripts. Like, we want it to be able to go and find all the things we hadn't yet thought of, right? Like, we want it to be really intelligent in that way. And then the last thing I'll say is, like, we didn't want to test models of this thing or anything. We wanted to test like the actual real code, right, in this testing framework, however we were going to put it together. All right, so those are kind of my objectives. Now we're going to go through each of those. I'm just going to say how we ended up getting there, right? So we want this thing fast and debuggable. What is the best thing to debug? Well, it's like a single-threaded program. Like, I'm talking to a bunch of engineers here. You know, you want everything in one thread. It's right there. Like, it's easy to figure out what just happened, right? So we want everything on one thread. Concurrence is always making things harder. Next, like, if we want to test the whole system and we want it all to be in one thread, now all of a sudden we're talking about having everything in a single binary. So this is where we start getting into where it gets pretty hard to run this type of testing, right? Because if you want your whole system in that one binary, now everything has to be homogeneous, and we can't have all sorts of other dependencies pulled in from everywhere. So that starts to get pretty tricky. And then for the robust thing, as I said, like, I don't want to have to hand script everything. I don't want to have to pre-think of all the, so I want this test to be really randomized, and to add a lot of sort of entropy in where I wouldn't have guessed that it was needed, and that sort of thing, right? This is going to be like a very robust, very powerful testing system. And then for the real code, Rust, was Rust around in 2010, by the way? No, it was another 5 years before the first like prod version of Rust shipped. So we were building this in C++. So we wanted to have like a literate style where we were able to like have the testing sort of baked in and the distributed aspects baked into the software writing in a very literate way without having to do anything crazy. And we wanted to be in C++, right? So how do we do that? So this is my last little piece. I'm going to tell you how each of these 4 things kind of came to be. So the first thing for the DST is it has to be deterministic. And this is what we get when I said it's easiest to debug things when they're in a single thread, right? So the deterministic piece of this means that like we're going to have a single thread, deterministic event loop, and everything happens in a predictable order, and we can rerun any test we want, right? So this is going to be very powerful. The next thing is, if we want to have a single binary, but we also want to be testing a whole system, now we're going to have to simulate, right? Because the actual distributed system isn't a single binary, and when we launch it, it's many instances, right? So now we're going to need a sort of some simulation within this thing. And so that's where we have the deterministic and simulation. And when we say simulation for this kind of thing, we often mean network simulation, but also, we can simulate multiple threads running or multiple processes running on a single box. There's a lot of simulation you can add in, especially when you start looking for faults and that sort of thing. So the next thing is we're going to inject entropy, as I said. So we're not just going to run the same scripts each time. And I'll talk a little bit more about kind of like how we had to hand tune some of this stuff. But when we're running these, if it's fully deterministic simulations, and we just do the same thing every time, that won't be very interesting, right? So we have to be like very careful about how we inject this entropy. And I think we did a pretty good job on it with FoundationDB. And I'll tell you a little bit more about how we've like evolved this approach a lot when we talk about antithesis. It's come a long way. And then for the last thing, and this is why I asked about committers, if you've written any code in FoundationDB, you know about the flow language. So we came up with this DSL, domain-specific language, that you write in Flow, and it's sort of like transpiled to C++. So this is my first, I promised there was to be like some historical picture. So I don't know that the next thing you're about to see is like anywhere on the internet, okay? When do you see something that's not actually been on the internet before? So this is a picture of a sheet of graph paper where we drew, see now it's on the internet, where we drew the initial design for Flow. So you can see there's like code blocks and statements, and I can't quite see it from over here, but on the left-hand side, I think it says like an actor, and there's state, right? So this was like a graph paper design for what Flow was going to be. So does this still look like that? So I went and grabbed some code from GitHub. This is like the master server or something like that. Just went in and grabbed a random function in there. So see the actor keyword still there. See the state declaration still there. Wait statement still there. So you know, the language is still working kind of like it looked like on that sheet from 15 years ago. You also see an interesting thing where we send a thing called never. So there's a lot of like baked in sort of like distributed system concepts that are right here in Flow. And this domain specific language is not always the way you start when you start a new project by writing a language to write the project in. But sometimes if you know you have like really specific requirements and you know that you're going to be pretty crazy about the testing, you go in and make this investment. So this is a little picture of Flow. All right. So how did it work? Like in reality. Now, I have a little bit of a picture from this. I haven't been involved in the project in a while, so I'm sure that there's still tons of simulation tests and hours being spent on it. I would say that by the time we were, you know, at the end of our time as an independent startup, I think we probably ran like 3 million simulated hours a year. So we were able to simulate time running faster than real time and things like that. So when I say simulated hours, it's probably less than that in terms of like actual processor hours, core hours. But you know, to the point of like, could we run it more than our customers? Well, I don't know that we really could, but we were able to run a really large amount effectively of FoundationDB in this like interesting clustered situation. So the key thing here though is like the faults that we were able to inject as we ran it meant that these hours, like 3 million hours, they weren't just like 3 million hours of happy traffic going back and forth, sort of like steady state. It was like 3 million hours of like faults being very particularly injected to get to the most interesting pieces of code. So I think I'll come back to this later when we talk about randomized testing and stuff like that. But you know, that was actually kind of a major investment, right? Like I don't want to say that that was something that we were able to just like set and forget. We really did have to kind of, as we built new features and as the simulation evolved, kind of go back and make sure that the simulation and the faults were actually like really triggering all the behaviors that we wanted. So, right, what else did we have to build? If you go on GitHub and look at the project as it exists today, under FDB server, there's this whole workloads directory. And that workloads directory was there from, the first year I was working on the project. And those things have been built up over a very long time, right? Because a good workload is the thing that lets the test really examine all the features that you want it to hit, right? So we did a lot of work on these workloads, and a lot of work trying to optimize them to hit all the behaviors that we wanted. So there was a lot of investment that had to go in that. And as I said, there was like continuous improvement. What I like to say about this is like there was like a brute force, sort of like a tuned brute force approach to search that we did on FoundationDB, right? Each run from beginning to end of the simulation was set with a seed, and it would run. So because it was only brute forcing through just choosing different seeds, we had to make sure that each seed that was chosen was likely to be something pretty good, right? So there was no true search within a simulation run. Rather, we had to be very good and very smart about the distribution of what we ran. So there were fast tests, there were rare tests, there were things that were very expensive to test, we'd run less of, and then things that turned out through basically just science. We analyzed what we had found and found things that were like pretty good and pretty cheap at finding bugs. So in the end, like, I think this was my last count. Now maybe there's been more, but we found very, very few bugs. Customers found very, very few bugs for us in production. So I think in the end, like, it gave a good reputation to the product, but also it let us move pretty quickly. Like, we knew we were shipping high quality stuff. It didn't have to spend a lot of time on support. Okay, so my next little thing. So how do you think that we made sure the simulation actually worked? Like, was it simulating properly the real world, right? Like, maybe the simulation, it looked good on paper, but then when we actually ran the thing, it hadn't really simulated all the failure conditions we were going to see, right? So you're going to see an amazing woodworking project, I think by one of the founders. So we built this little cluster that we called Quicksand. As we didn't run a lot of tests on this, but this was like the actual sort of like, check. It was what's testing the tests. We had this networked power supply, and there was like 8 little machines there with a little SSD in the middle and some like hilarious like plywood chassis that the thing sat in. So after getting the simulation up and running and working well, and this was pre-customer, we then and I see some smiles from people who know kind of like the FoundationDB and Antithesis ethos, like going all the way down to the details. So we ran this thing, and in fact, an early version, the very first version of FoundationDB included Zookeeper as a dependency, because we decided that we didn't want to deal with the like consensus and all that stuff. We're going to deal with the transactional layer, right? Makes sense. So in our simulation, we wrote a mock of Zookeeper, and again, I don't know Zookeeper from now, but Zookeeper 15 years ago, read through the docs, tried to create a mock very carefully with all the edge cases that were appropriate for its API. And it passed, did well in the simulation. And then we loaded the thing up in here, power cycle it maybe once or twice, dead. So we went back and got rid of the Zookeeper dependency and wrote our own Raft implementation, or no, disk Paxos. That's right. We wrote our own Paxos. It was 15 years ago. We wrote our own Paxos implementation, and we never had a problem with it after that. So this did actually sort of like verify and found a very important reason why we needed to be really building all the way down to our own sort of consensus protocol piece. So anyway, when we went to scale up, we bought some machines. This is just on the floor of our startup. I thought you guys would want to see pictures from way back. This is the original like FDB cluster, basically. So we bought them to like do perf testing. But then here's the great thing about sort of like randomized testing, like deterministic simulation and other things, is you can just like run more tests, and there is marginal value. Like if you test for 2 hours instead of 1, it's like twice the value, right? Well, maybe there's diminishing marginal returns. But because they're randomized, you run another test, you spend more time testing, and you actually get better results. You get more confidence. So when this thing wasn't running our sort of like perf benchmarks, we would just, every night, or during the day as we were working, we would just have this thing churning through simulations and just doing more and more hours. So we kept that rack pretty busy. So if you want to go for like the real deep dive, Will, who's the CEO at Antithesis, gave this like, very highly referenced talk, frankly, a number of years ago at Strange Loop. So he goes, this is a longer talk, he goes really into the kind of the nitty gritty of the simulation testing. So absolutely would recommend that if you want to go deeper. All right, so on to the second section. So in practice, I don't think I can say that we invented deterministic simulation testing, but definitely popularized it for sort of like mass market database distribution development, I could say. So where were they used today? I did a quick survey. I would say, like, I know for sure, we know the Tiger Beetle folks pretty well. Bunch of databases are, and in fact, when I was just going back and looking for this, Kafka, actually, do you know what craft was written to replace? Zookeeper. So Kafka went back and wrote their own sort of like Zookeeper replacement and advertised it as being tested with deterministic simulation. So, a lot of mentions of things, I'm not familiar with all of these projects exactly, but quite a few people are saying, especially in the database space. Actually, I guess I could ask this room, anyone outside of FDB doing deterministic simulation testing? No? Okay. But I think another cool thing here is there are some libraries that I don't know if they enabled some of the projects there in that previous list, but plugging into the Rust ecosystem, Turmoil and MadSim, I don't know, I have not used these myself, but there are people out there that are trying to make this available to others through. So if you're, again, these are in Rust, I think it attracts a certain kind of person that wants to get things really right. You're programming in Rust. But these are libraries that plug into Tokio and do this like deterministic simulation testing. So again, if you're ready to say, I'm going to be willing to have a single thread, I've got my entire system in Rust or whatever, and in this one binary, then there's libraries to help this actually work for you. All right. So I'm going to move on to the test your software piece. So folks ask me for advice on software testing, which, sometimes I find it funny because I feel like I'm still learning and figuring things out as I go. But what I'm going to do is I'm going to kind of give you my recipe. So I'm going to give you my 4 top things. And they're going to kind of a little bit correspond to the 4 things I mentioned earlier. And we'll kind of go through here. I have my own opinions, so maybe in the questions section you can challenge me and tell me I'm wrong about some of this stuff. So I'll go through these at greater length. Number 1, I think this is like easy. I say minimize cycle time. So I'll go through what I mean by that and how to get to it. But it's always best to do more testing, and you can do that by minimizing cycle time. Now I'm going to get into a controversial one. I'm talking about dependencies and mocking them. So I think this is an interesting area with not one exact right answer. So I'll dive into a little when I think you should and shouldn't. This is, I think, oh, sorry about that. Lean into the mic. Adding randomness, this is like, I think, the best like pro tip for how to go like level up your testing game. So we'll talk a little bit about like the approaches to randomness and how you can add randomness to your testing. And then just a little, basically housekeeping. I think test validation, and we can go back and look a little bit at how it works in FoundationDB, and I'll mention a little bit of how it works that those tests get validated. All right, so first up, cycle time, and with the obligatory XKCD comic, I don't know if you guys remember this one. So the best way to say when you're goofing off, I'm going to replace it. My code's testing, right? This thing is at least in test. You can say, okay, I don't have to be the keyboard. So obviously it's a joke, but we we can tell that there's like time waste happening here, right? So this kind of gets to my minimizing the cycle time thing. Why? Like, obviously, we want to test more, but I think really the key here, in my opinion, is like the lower latency, right? Like the lower latency you can get in your testing loop, the better you can test the stuff you just wrote. And by far the easiest bug to fix is the one you just put into your code, right? If you think about it, at the limit, it's like the little squiggly line under something, and you're like, oh yeah, that was not a variable, or like I mistyped that or something, right? That's like instant feedback. And you don't even think of that as testing really, but the closer we can get to that instant feedback. So the minimizing cycle time, important for more tests, but really important for this like feedback latency, I think. All right, so that means I'm going to give you, so if you remember nothing else from this presentation, my next line, this is like my best pro tip, all right? So you should always use the time that you're waiting for tests to make them go faster, all right? I love this piece of advice. It's like whenever you're waiting for a test, just go work on that same test and speed it up. So why is this a great piece of advice? Well, I think making your tests run faster is always good. But the best part here is like when you have slow tests, it means you're going to have a lot of time to work on making your tests go faster. And then as you get better and better and your tests are faster, then you have less time to work on them. And that's fine because like your tests aren't taking very long at that point, right? So it kind of like it's a great sort of one-size-fits-all piece of advice. If you have fast tests, this won't give you much time. If you have slow tests, you have a lot of time to work on it. So this is something that I try to remember when I'm doing my development. I tell my team, you know, we can always work on speeding tests up by working on that while they're running, right? So that's maybe my number one piece of advice to take away from this. All right, here's something that's I think a little bit, I have a personal feel about. Maybe this is like my hot take here. Testing, wherever possible, should not be behind some like commit and push gate, some piece of workflow where you have to push your code. Now, I know a lot of you work professionally in some area where like you just have to, that's just like you've got to push your code and it kicks off various like testing, but wherever possible, this just adds latency and adds a bunch of burden and mental overhead. It's just like wherever you can possibly set your tests up so you can just do your build and kick off your tests, you're going to be happier, right? So that's my other thing. And again, I know that sometimes based on your environment, it's unavoidable, but that's something else to kind of like keep in mind as you're thinking about how you can level up. All right, so I'm not going to belabor this too much, but we're going to talk about kind of like the inner loop as I see it of getting your work done as a developer. Like number one, we write the code. Like this is the fun part. It's the part we get paid to do. Like, right? This is the good stuff. But that's really only one box in like a long cycle of things. We have to compile the code, right? So that takes some amount of time. And the compiling, you know, it might sound kind of like archaic, but it is like a very real step. Not always the slowest one to start off with. And then there's kind of like the testing thing. Test has to get launched, test has to get set up, and then we finally get to the meat of like, what do we actually want to be testing? Like, how are we actually touching the code that we just wrote, right? There's that last hole, and the last thing I think is parsing the results. So this can pull in a lot of things here, and I don't just mean like parsing like machine, like parsing things. I also mean like you as a person, like how do you take in the result of the test? How do you parse it into something that you can go take action on, right? So you know what to fix or what's not right, right? So like this is a non-trivial amount of time that can be spent on this, and I think we can work on all of those, right? So like how can, I'll color code this thing. Like the green parts are good. Like we want to write code and we want tests that are testing that code. And so like we want to go and attack all these like orange areas. Couple things, you know, like that I've seen work and something that we're doing at my company is like for compilation time, like have parallel processes that do sort of like the fast compile with no linting and no optimization. and the slower compile, and then just run the test on the thing that compiled fast and keep an eye on the sort of strict checks and the slow compile, but don't let the test actually gate on that, right? Then you kind of get the best of both worlds. Like, it's almost like having a fork where there's one part of your test is the slower compile with all the linting, and there's another part of your test is like the fast piece that actually goes and runs the rest of the test, right? So that's something that we've used a number of times to speed things up. Like, even we do this with ESBuild in TypeScript. All right, then the launch. This kind of gets back to my commit and push gates in the testing loop. Like, the faster you can just get the thing launched, the better. If you have to push it, you're adding a bunch of time into your loop. Setup. It's funny. I was just talking about this with somebody today. Sometimes we see people in their test setup, they want to load like a huge slice of prod data. They want to put like 30 gigs of data in. It's like, okay, well, you might want to have some environment where you get like a whole slice of your prod data and put it out there. But if you want to run fast inner loops, you should not have 30 gigs of prod data, like, or some snapshot or whatever. Like, find some minimal way to like get just a smaller data set that's going to be important. Like, put some thought into it, but try to get some minimal piece. And this is something I tell customers of Antithesis is like, try to be really targeted about what data you're putting in there. It's going to save you a bunch of time, a bunch of compute, right? And then the parsing. This is like, stuff we struggle with all the time, but like, do your tests show conclusive results? Like, when you look at the results, can you actually tell, did the test pass or fail, right? Like, flaky tests get in the way of this. Also, like, this is the reason for, like, if you've heard the phrase, like, living on green. Like, if you and your team are all developing stuff and some of the tests are like known to be failing, but you're not sure which ones, and some are failing for you, and then you have to coordinate on your team. So the quicker you can have hygiene around this, and know kind of like quickly, okay, I know what should fail and shouldn't fail. Hopefully we're living on green, and then we can quickly parse the results. So this is all standard stuff, right? I'd love to hear from you later on your approaches to this. All right, so mocking or not mocking. So I told you the story about FoundationDB. We mocked out a dependency of ours, got us in trouble. So should we mock things? Should we not? I would say, like, really, the question is, like, is this a unit test or an integration test? If you're writing a bunch of unit tests, like, don't put a bunch of mocks in there. It's not testing the actual important thing. It's going to slow you down. Is your mock of Postgres? In fact, it's actually fun. I was talking also about this with somebody today. Subtle concurrency bugs in your database are not going to come through in your mock. So, like, if you're writing unit test, strip it down, no mocks, make them as fast as you can. But if you have integration tests, like, a way to make an integration test useful without needing to pull in your entire infrastructure is to have smart things to be mocked out in it, right? So I think there's a balance here. I know that when we are testing our own software, we use Antithesis ourselves to test Antithesis, self-hosted. And so there are cloud dependencies that we mock out. So when we can test our whole thing in a very neat package, even though at production time we're using these other cloud services. So I think there's an important time to mock and an important time not to. And then the last thing on sort of like, are we sort of like creating, how much of a simulation are we creating, I guess I'll say, is like, how much are we mocking out? This is where, when we get to the lowest level, you can use a DST library. There's also like higher level things, packages for mocking dependencies out. We use local stack ourselves, recommend it, to customers that are trying to like get a production-like environment up. But there's like good alternatives for running a meaningful kind of like local integration test. All right. The third area, randomness. So this is a fun one. Like, as I said, I think this is like the probably number one way to just like level up your testing game. So obviously we don't want to be testing the same things over and over. And as I said, the more randomness you can get into your testing, the more just like running more cycles means that you're getting more value out of your test, right? So each test can add some marginal value. All right. So this is my high-level advice. I would say when we're trying to figure out like how to add randomness, there's a number of ways, and I think the top two are sort of like fuzzing and property-based testing. If we are writing something that's like we're defending, right? We want to write something. A great example is like a JSON parser. It's going to take untrusted stuff off the internet. Like, yeah, you want to be fuzzing it. You want to be putting absolutely every possible input into that thing you can imagine, right? Valid and invalid. And you're not so much concerned with like the correctness of the parser, but you absolutely want to make sure that there's no set of bytes that can go into that thing that will make, they could have undefined behavior or whatever, right? So I think if you're thinking about defense, you're thinking fuzzing. But if you're thinking about correctness, I think property-based testing, and this could be its own talk by itself for what it's worth, so I'm not going to dive super deep into it. You want to think about property-based testing when you're thinking about correctness. So what is property-based testing? Who's here is familiar with property-based testing? Okay, got one hand in the back. The idea is like developing a set of ways to automatically generate sort of test cases or data sets, usually something small, with corresponding properties about them that can be verified against them. The trick here is you want a set of properties that are sufficiently sophisticated to tell us something interesting about the algorithm we just ran. So like, unlike fuzzing, we're not just passing random things into an algorithm to make sure it doesn't crash. Rather, we're able to define something about that data that we just sent into it. So properties are very useful for testing kind of like high-level guarantees about a system. So this is how we tested a lot of things at FoundationDB, and how we talk about testing a lot at Antithesis with our customers is like, what kind of high-level properties can you say about your system? Like maybe it should always do something, or maybe it should never do something, or maybe it should sometimes do something, right? So by defining these properties, we're able to have like a global view rather than just on a certain exact thing. Then we can add randomness and see at that global view, did the system do what it was supposed to according to the properties that we define? So again, that could be a whole separate topic and talk, but I think it's a very, I'd encourage you to go take a look. It's a very, very powerful approach. Okay. This is, I said I would also take a little, some other pieces from FoundationDB. Who has seen the word bugify in the code base there? Yeah, so another thing that we did is we want to add, when you're testing, we wanted to add faults in, and we did that. We injected faults in the simulation. But this approach is just like, sort of like taking a function that would normally, have a best case operation and fulfill its obligation in that best case, and then sometimes in testing, do a thing intentionally that's at the edge of its obligations. So my favorite example from FoundationDB here was when a transaction committed, it could return like yes, like committed, no, like it was definitely rejected, and maybe. And so sometimes in the test, when we had a transaction that otherwise could easily have just committed, we would just actually commit it, but then return maybe. I mean, we knew it would committed, but if in the case of bugification, we could just say, well, we're allowed to say maybe kind of whenever we want. So we'll just go ahead and say maybe. This is a way of like, okay, and again, it's important that it was randomized. This is a way of sort of like pushing the system at times out to the edges of what it should be able to handle, right? So you can imagine things that sometimes are allowed to return an error, but wouldn't normally, sometimes returning an error in your tests, right? So that bugify thing, and you can go look through the code base on GitHub. You can see links to that bugify construct. But I think that was something that we used quite a bit. And in fact, it's funny. This was in one of the alpha versions, I think. Couldn't tell you which one. We had a mistake where we shipped with, in the client, Bugify set to on always in the production build. So it actually worked fine. Because again, the Bugify did not actually violate any constraints on the database. It only sort of like would reject some transactions that could otherwise have succeeded and stuff like that. So we found it pretty quick, and we never made that mistake again. But that's a little interesting piece, and I don't know if you can go download that alpha, probably not anymore. Okay, so this is item number 4. This is kind of the last one, test validation. You know, when we write a test, we're pretty sure it's going to be meaningful, I guess, for the thing we just wrote. But how do we know in perpetuity after that? Is the test going to remain useful? Is all the code that I know that got tested when I wrote it, is it still getting tested? So what do we do in FoundationDB? Back in my day, we called this the test macro, but that was a bit ambiguous as to what it did. So it is now renamed the code probe macro. But the idea is, you know, what we would do, and again, I don't know what the numbers are these days, but leading up to a release back in the day, we'd run like 100,000 simulations over a weekend. And so we wanted to know, like if we look in aggregate all over all those simulation runs, like what code paths did we hit? And you know, we could look at straight code coverage metrics, and probably you should, like it's not bad. But what's much, much more information dense is littering your code with these little probes and sort of these like breadcrumbs, right? Where you can go back and say, okay, not only did I get to this part of the code, but in this case, you can see there's actually like, and I forget where I pulled this from. I went and grabbed this up GitHub. You know, there's actually a condition, right? This, you know, there's some actual number of things in that list or whatever. So, and with some name associated with it. So when we would get back on Monday, look at over the whole weekend, run hundreds of thousands of tests, we could say, okay, we're actually hitting these things that we know we should be hitting. Apparently now you can mark things as rare. That's new technology to me, but you know, we knew some things should be rare and we're hitting them a few times. That's fine. We know some things should be frequent. We're hitting them. And then we would have just basically a ledger of all of we would scan the code and have a ledger of all the things that could be hit. And that was really the important thing, because we could tell what code probe macros we were not hitting, right? So just like the, you know, test can easily, just like your comments around your code, can easily diverge from what they were originally supposed to do, right? So this is just like a way of thinking about, okay, when I write my test, are they good the day I wrote them? And are they good a month later? Are they good a year later? Now, there's another thing here, feature flags. Like, we don't ship with feature flags, but I know it is something where you can have a code base where you test with one set of parameters, and then it goes into prod and different parameters get turned on. And all of a sudden, you're now in a world that you didn't test in. So feature flags are very powerful, and a lot of people get a lot of value out of them. But it's just kind of like another thing that I'll throw out there, which is like, it's very easy to test your code, but not have really fully tested, not the way it's going to be tested in prod. So, you know, being able to track, okay, have I run my code with all the other feature flags turned on or off or whatever it's going to see in prod, I think is also another thing to keep your eye on. Okay. Last section, or antithesis. So I won't belabor this too much, but you know, what we did is, you know, some of the folks involved in FoundationDB sort of like based on a bunch of our insights and work there, like, well, what if we could take some of these insights about simulation and, you know, randomized testing, but make it like much powerful, like with some real search, basically, instead of brute forcing, and make, you know, package it up and make it available. So I think the things that we really think are important for our users and folks that are, you know, thinking about antithesis is that you can simulate your whole stack, right? So instead of just simulating one piece or whatever, it's a way to get a lot of sort of non-homogeneous things together in one simulation, run it together fully deterministically, and then inject faults in some really smart way that aren't just injecting random faults, projecting faults smartly to literally search your code base for bugs. And so, when we put this all together, I think it's a way for a lot of folks to level up their testing game in a bunch of the areas that I just said, right? Getting to your complex bugs, finding bugs soon after you get them into your code base, getting great fault testing, and being really sure that it's testing for bugs you didn't even think to test for yourself. Great. So that's Antithesis. That takes me to the end. So I'm happy to field some questions, whether it's about some history thing or Arvind, how do you want to run this? Do you want to just have people?
We can have people raise their hands, and I can have someone run the mics out to them.
Okay. Great. Yeah, I don't know how long you want to do this, but just yeah. Okay. Okay. Great. Do you want to introduce yourself just super briefly?
Yeah, I'm Jay Prabhakar. Yeah, I do formal verification from my startup, but this question is about the stuff only.
Okay.
So you mentioned about randomness and also being able to execute the tests fast, right? Now, whenever as a developer we make change, we want to. It's nice to see that I ran all the tests are complete, but with randomness there is no such thing as complete because you can have different seeds that can go on forever.
Yep.
So how do you time box it, or is it like we set it for one seed and say that it's good enough, let the continuous catch the bugs?
Amazing question. Yeah. Great insight. Yes. I will say when people get into this world, and they're coming out of a world where they have a test suite that they run, and they I ran my test suite and it passed, right? And then you go to doing some more randomized testing, and it's well, I ran it for an hour and it didn't find anything. So is that passing, or is it 2 hours or 3 hours I need to run? So I would say a lot of this is just getting to know the system that you're testing it under. I mentioned that we would run it over the weekend. It was 100,000 test runs. We also knew that we would kick off at FoundationDB in the early days, we'd just kick stuff off as we were working on it during the day. And we knew after running for 5 or 10 minutes, we'd get to, maybe 200, 300 simulation runs pretty quick. And if you didn't have any failures in that, it was probably good. You just put it into the nightly stuff and go test it there. And, if there was something truly wrong with your code, you were going to see it in the first, 50, 100, 200 tests, right? So there is a certain amount of knowledge. One of the really cool things that we've been working on, and we'll talk about more over the coming months, is just this concept of findability, using a lot of statistics to figure out how hard it is to find different bugs, and therefore kind of get different levels of assurance after different amounts of compute as to how gnarly of a bug would I be able to find with this. So yeah, I do think it's very insightful, and most people when they get going with this just have to develop essentially a sense of how much testing needs to happen. And I think for us, people aren't generally testing only with Antithesis. Usually they have something else they're testing with, so they're able to kind of ramp on, compare the two, and sort of see, okay, here's the relative amount of effort it takes to get to I don't want to say parity, but finding the sort of bugs I'd want to know that I was finding. So yeah, it's a real hurdle.
Dominic from CDDB. I have a question to your testing for transactional stuff. The thing is when you have a high workload which has 1 million of transactions per second, and you observe, you drop down your transactional rate because the observation takes you computation power and basically will change somehow the code paths which will it take internally. How do you ensure that your testing is basically not hindering all the basically code paths, and how can you basically make all code paths work?
Yeah. I mean, I don't know if I'm quite exactly parsing your question, but I will say this, like when I mentioned this sort of code probe stuff, this really gets exactly that, which is like we want to notate basically all the major code paths we want to be taking in our system and make sure that we're hitting them at least with some regularity. So, you know, you were talking about sort of like high traffic prod and testing happening at the same time, which was not something we were doing with FTP, to be clear. But if the question gets at like, how do we make sure that we're testing all the different code paths that are like really meaningful, I think that's where the sort of code probe approach.
The question is basically like, when it's not that fast anymore, I might be having a hard time to actually go into that code path, or it might be even impossible to go into that code path.
Yeah, in FTP, you'll see a lot of things where bugifies are used to delay different responses to things. So there's often like delay with probabilities and a lot of like jitters added to different replies. Actually, we add jitter in all over the place just to make sure we don't get a thundering herd problems in general. But definitely slowing down responses with bugifies if they weren't already directly slowed down through the fault injection. So yeah, I mean, I think getting at all of these different code paths is tricky, but through a combination of like really directly trying to slow them down with bugifies and then injecting of the faults, I guess how we were able to get sort of like really complete code coverage.
Hi. First, wonderful talk. Thanks for the insight. This is Atta. I work for Snowflake. I have two questions. One is I felt the Bugify, even using it, is a very powerful tool. Want to learn a journey of how you find that where all the Bugifies needs to be put for getting the full coverage, because even definition of full coverage for such a system is actually kind of pretty interesting. So
yeah.
What was the journey of when you say, was it an organic that, you find that this should be bugified versus this should be not? And my second question is around the performance testing. So this is good for the correctness part of it, but when it gets to performance, how would you say that the new code is not slowing the commit latencies down?
Right.
Everything would work in a tangent for the correctness. Okay.
Yeah, a couple things on that. Two great questions. So I guess my best answer for like where are the bugifies put in, and yeah, I'm glad you've experienced them firsthand. It's a very powerful way to do things. They assist in sort of like the code probe. Like sometimes you want to have a bugify to like get into some code path that simple fault injection won't get you to. But a lot of it is just like kind of a development philosophy. Eventually it got kind of baked in. And if we're writing some new, RPC call or some new method or some new thing, we're like, what kind of crazy thing is this allowed to do? And then let's like try and make it do that thing. So some of it is just like kind of like muscle memory of learning to put it in different places. So I will say, I do think that it grew up over time. We added it intentionally in a couple sort of smaller situations where we're like, okay, like I said with the commit, like sometimes you want to like, definitely commit it and return a maybe, and sometimes you want to not commit it and return a maybe, so the person has to go back and actually check. And that was just something where like, this makes sense, we're right here at the logical decision point, let's just add some code that like, makes this, returns maybe, But we went back and added a lot of things. We found different code paths that were like harder to get to. So to your second question about performance testing, very, very good. So we never ended up doing performance testing with this approach. So like a little bit of history is we definitely toyed with it, like creating some, if you have this simulation, maybe we could take our simulated disk, and there's a simulated disk if you dive all the way down, and sort of like say, okay, here's, the latency for reads and, keep track of where all, the read orders and seek latency, and sort of like develop a super high quality model of the performance of the underlying system and then use the simulation to like almost like prove that. We never really went down that path super far. It seemed like it was going to be pretty tricky to get a simulation so accurate in that dimension it would just do the thing that we wanted in production. So I showed you the picture of those machines sitting on the floor instead of in a rack. I mean, at some point we bought some machines. We're like, okay, we're just, they weren't even top of the line, but we're like, okay, every night we're going to test with the exact same hardware and really look for regressions in performance. So, I mean, the simple answer there was like, we toyed with some like kind of crazy thoughts about it, but decided that the simulation had enough of a role and enough of a job. We didn't want to overcomplicate it to add a new entire dimension to it. So yeah. And for what it's worth, that continues to be the case at Antithesis. Most of our customers are not doing, even though they'd probably like to, are not doing like performance and regression test, like performance regression testing, but working on sort of code, sort of correctness testing.
Hey, Ben. Great talk. This is Chinyu from Apple. I'm working on FoundationDB. So my question is, we use FDB. It works great. One of the problems we found in production is the control plane of the service is as important as the service itself. Mm-hmm. For example, if we use workflow system, we use the Kubernetes operators. And if this system having issues, it's affecting our production. Do you have any comment on testing this control plane for the great service?
Right. I mean, I feel like you're trying to pitch Antithesis for me here, Jingyu. Obviously, the limit, right? So to extend that a little bit, by the way, to go the other way up this, because you went down the stack. You said, here's FoundationDB, and the stuff under the stack affects whether or not it actually worked. Well, guess what? The stuff on top of it, your application, if you do that wrong, it won't work, but not because of any responsibility here, right? So we always suffered in this sort of pure DST, pure sort of like single binary homogeneous approach of not being able to test the things underneath it and not being able to test applications above it. One of the reasons that we have that FoundationDB, if you're familiar with how it works and is distributed, there's like a thick client that's distributed that, like you have to link against. There's not sort of like native libraries in different languages. And that's partly because the client, which runs on, not on the server, but on the client nodes, is part of the distributed system and like really needs to be tested in the simulation with everything else, because it has a lot of, has to know when to retry and what nodes to connect to. And I mean, it's a very, very complicated piece of software, just as much as the server. So that is built in a certain very specific way to do this. So I think, and this is part of the reason why having a much more general thing, like, sort of like a generalized hypervisor where you can load all sorts of software together into it and test that together is important. So I don't know. I guess all I can say is I agree. One other thing you can note in the FoundationDB test is that, like, we try to test as much of the thing as we can, but if you look at it, the network is simulated, so that means we're not actually using the like Linux networking calls in the simulation. But when you boot it up in prod, well, now you're talking to the actual network, right? So there are these little bits around the edge that, like, you want to simulate, but if you're going to do this in process, sort of in the user space, you're just not going to be able to pull all of that code in, right? So it is tricky, and that sort of continues to be like one of the things that makes the FoundationDB test a little tricky, right? Love to pull in the application, love to pull in the control plane.
Okay, yeah. So when it comes to some invariance in Antithesis, you mentioned 3 terms: always and never and sometimes. Mm-hmm. But there are some properties, say liveness properties, like eventually, mm-hmm. like given enough time, eventually the data will become consistent. So do you have those type of property specification?
Yeah. Those are things you're going to see movement on. I can't tell you exactly when over the next little bit. I think questions about sort of like a timeout to say, like, okay, if this happens, then within 30 seconds or 60 seconds, and particularly like if we have no more faults, the thing should come back. And also more sophisticated properties, which if you look at the SDK for Antithesis are tricky to define, but they have to do with like series of events. Like if I see A, then I should always see B, and then I should sometimes see C or something like that. So this is very important, I think, to be able to define these types of very complex sort of like, you know, dependent bugs and sort of like causal relationships over time. So we are going to make it possible for eventually for customers to define those in time. So yeah.
Good. Yeah.
Hi, I'm Ilya. I work for DoorDash, and I'm focused on experimentation. And I was just wondering, so you were mentioning that you're primarily were focusing on kind of simulation testing on your development environment, and why didn't you explore actually testing in production, meaning that you have, you know, a real production cluster, and then you try testing your, you know, in this case, database in production, and things, for example, I don't know if you heard of Chaos Monkey, where you try to intentionally, you know, shut down your dependencies and see what happens with your real system and things like that. That's the first question, and the second one with, you know, things like feature flagging or experimentation, A/B testing, where you have, you know, different algorithms that you potentially want to do. How do you, you know, have you explored, you know, those variations where you want to randomize how, you know, different code paths that would be randomly distributed within your database?
Going in reverse order, definitely when we're working with folks at Antithesis, we're like telling them, hey, you know, either make sure you can tell which flag was active and when in a test, or help us from our active search side control that, right? So put that, if you can somehow get that in our control, and we can more actively explore and turn that into part of the search space, and we can really like go after those differences. And then to your first thing about like testing in prod or whatever, I guess what I'm reading into that is I showed you that like quicksand cluster or something like that, and you're saying, okay, we had that quicksand thing, which was like clearly just like trying to push the limits of what a real cluster would be. There was the simulation, then there was the real thing. Is that kind of what you're saying? And like what in prod, what was the testing approach? Now you're reaching, I had to reach back for memories that are a little distant. We did not do sort of like chaos monkey style tests generally. But I will say that one of the approaches that we took with FoundationDB is trying to escalate any problem we could find into like the process crashing. So like this was like very actively done so that whenever some like unknown situation would occur, and I don't want to paint too broad of a picture. We had like error handling code, but like when things like ended up being a tricky situation to recover from, we would just have the node crash. And the reason we would do that is because we were very, very, very sure that the system was reliable for nodes going down and coming back up, because we had tested that so much in our simulation. So that was one way that we, like, by making the situation sort of worse, we actually got into a regime that was much better tested for us, right? So this is kind of like cutting against the grain of the other thing where you try to like make your software robust to every possible thing so that it like never crashes. Well, we just said, hey, we're really good at handling crashes. The thing can crash anyhow it wants, anytime it wants, and we're going to be able to handle it and come back. So rather than go and harden our process so it like never crashes ever, we'll actually opt to crash. So, you know, you get into a situation where if you're too, you can take that too far, because if you're too eager, you can get your whole system coming down pretty quickly. But that was another thing that we did that gets a little bit to like how we thought of production, sort of like mimicking as close as possible the simulation environment that we had. And then when we were really running it, I mean, we could tell war stories about running this thing actually in prod and, finding, bad hardware. I mean, production creeps up and can bite you. So we learned a lot getting this thing in production at large scales. It's probably a whole nother talk there. I don't know if I'd be allowed to give that one, honestly.
Okay, I think we're sort of on time. Maybe we could take one last question before we wrap things up, if there's one.
So I'm Nicole. I'm so on the Apple FoundationDB orbit, and I was wondering if what you feel about the trade-off. Like, to me, when I'm reading like the Bugify injections and other really useful testing devices, I feel like there's a trade-off between readability and like testing, and I kind of feel like, I don't know, how do you feel about that? Because there's something to be said about like if the programmers can't grok it as quickly, there's some loss of testing there. Yeah, how do you go about that?
I mean, I did, at the very beginning mention like readability and sort of literate coding as like something that was important in order to sort of like write good code. You want to be able to write code that's easily understandable by yourself, and the people that come after you. Yeah, I mean, I guess if you look through the FoundationDB code base, like it is, there's a lot of bugifies and it's not a simple code base. I mean, definitely not a simple code base. So yeah, I think that probably cuts against it. The way that we did try to make things as clean as possible in terms of like some of the stuff we did there. I think there's also various bits of sort of like intelligence built into the way like the simulated network works, et cetera, that like kind of comes underneath that sort of like, programmer level that's the developer on the actual database itself. But no, I agree. Like you can get code too littered with test statements. So it's important to kind of like make sure that doesn't get out of hand. So I don't know how the clear sort of like this was our like, the rule that guided exactly how we did it. But no, I think that like keeping things parsable by normal developers on a daily basis is definitely important. So, all right, well, yeah, it was great to be here. Thanks for coming out tonight. It's a great set. You feel free to come and grab me afterwards and say hi. Tell me what you're using FoundationDB for, and maybe there's some question that was so hard you didn't want to embarrass me, so come and stump me afterwards. But yeah, thanks for hosting.
Well, thanks for. I just wanted to say thank you, Ben, for flying out here to be with us and sharing all this information. It's an honor to have you at the FTB meetup and present here. So big thanks to you.
All right.
Also, a big thanks to Sarah and Amplify Partners and Rohan for partnering with us and for trying to help the FTB community sort of grow further. And also a thank you to Jinyu from Apple, who's been partnering with us on this effort. So big thanks to all of you. And last but not the least, thank you everyone for coming here and making this a successful event. Really appreciate you coming here. I hope you took away something from the event. And if you have any questions afterwards, feel free to use the meetup group or reach out to one of the Adobe volunteers, and we'll try to connect you with the right people. So Ben, there'll be more questions via email.
Okay.
So thanks again, everyone.
Sounds good. Yeah. All right. Thanks, everyone.